Okay, so let me remind you what we were doing. We took a number field k of degree n and we identified it with q to the n by fixing a basis of the number field. In this q to the n, we take the image of OK, the ring of integers of k, and we want to prove that it is a lattice. So, we needed two tools to do this. One is the theory of norms and trace that we did 2 lectures back, and in the last lecture we reviewed what a lattice is and proved certain properties of it. So, let me remind you what a lattice is. So, lattice, so in the following, so let us say in q to the n. So, subgroup lambda, we were calling it lambda. So, let me use the same notation of q to the n is a lattice if it satisfies any two and hence all three of the following properties. So, what is the first property? Lambda spans q to the n. The second property is lambda is discrete in q to the n with its natural topology, and lambda is a free Z module of rank n. So, last time we proved 1 plus 2 implies 3, and I said 2 plus 3 implies 1 and 1 plus 3 implies 2, those two are exercises. Okay. So, I am not going to recall anything about it. This time we will finish the proof of our proposition that image of OK in q to the n is a lattice, and then we will consider what this lattice sits inside q to the n like, and whether that is even a well defined question or not. Okay. So, let us continue. So, recall the proposition. If a number field k of degree n is identified with q to the n, then image of OK in q to the n is a lattice. So, here is a proof. So, what do we need to show? We need to show one of these two of these three properties. Okay? And so, we are going to show 1 and 2, and that will automatically give us 3. So, that is what we are going to do. All right. Okay. So, we prove that 1 OK spans q to the n, okay, which is k, and 2 that OK is discrete in q to the n. So, we will not prove the thing about its rank, that will be the corollary of this these two things. All right. Okay. So, how do we prove that OK spans k? So, that is easy. Let alpha 1 up to alpha n be a q basis of k. So, this we can always do because k is a n dimensional q vector space, and we know that there exists m I bigger than 0 in Z such that m I alpha I belongs to OK. So, this is one of the things we proved about rings of integers, and hence m1 alpha 1 up to mn alpha n is a Q basis of OK, sorry, of K, right, and all these are elements of OK. Therefore, OK spans K. So, that proves 1. Okay. Now, we prove 2 that OK is discrete in K. So, this takes a little bit more work. So, what you do is you let, so now I choose elements in OK such that alpha 1 up to alpha n is a Q basis of K, right. So, in particular I can write any alpha in OK as alpha equals L1 alpha 1, so on up to Ln alpha n for some L1 up to Ln in Q. I do not know whether they are integers or not, they need not be integers in general, right? They are just rational numbers. Nevertheless, when I take norm from K to Q of alpha, I know that this is an integer because alpha is in OK. So, this is one of the properties we saw of norm, that norm of an algebraic integer is an integer, right. Okay. So, norm of alpha, another way of writing this is L1 alpha 1 and so on up to Ln alpha n, right. How do we calculate norm? Well, I take all the embeddings from K to C and then I apply it to this element of On. Another way of writing this, because my Li's are rational numbers, I can take the same product, but I can write it as L1 sigma alpha 1 and so on up to Ln sigma alpha n. Okay. Now, we do something which is conceptually maybe difficult to understand at the beginning, but this is the kind of thing that we have to get used to in this subject. So, what we do is we think of these Li's as variables now, and so I can write this as phi of L1 up to Ln as this product sigma L1 sigma alpha 1 and so on up to Ln sigma alpha n. Okay. So, think of this as a homogeneous polynomial in L1 up to Ln, okay, and coefficients which are linear combinations of products of these sigma alpha i's. But you see that this is the coefficients, because of the symmetry, the coefficients are invariant under embeddings of k in C. This means coefficients are integers. Okay. First of all, they are rational numbers. So, let me write it that way if you like. First of all, they are rationals, rational numbers and algebraic integers. Hence, integers. Okay. So, phi of x1 up to xn, if you like, as product over sigma x1 sigma alpha 1 and so on up to xn sigma alpha n is a polynomial with integer coefficients, polynomial in n variables. Okay. Now, I am evaluating this at certain rational numbers. Okay. So, as long as, so what I want to do is I want to show that as long as I stay away from certain neighborhood of the origin, I can never get an integer, right. So, if within a certain neighborhood of the origin I never get an integer. So, if let us say, so how many a homogeneous polynomial, this is a homogeneous polynomial of total degree n, and how many how many terms can this have? This can have at most n to the power n terms, right. Okay. And integer coefficient. So, if mod of each Li is less than let us say 1 over n to the n, but greater than 0. So, they are not yeah, I mean you can take not all of them 0, not all 0, not all Li's are 0, then phi of L1 up to Ln is certainly less than 1. So, mod of this is less than 1 and bigger than 0. Okay. So, hence cannot be an integer. This means that if you take alpha to be L1 alpha 1 and so on up to Ln alpha n with mod of Li less than 1 by n to the n and not all 0, not all Li 0, then alpha is not in OK. Okay. Therefore, OK is discrete. Right? That is what the definition of discrete is. You find a neighborhood around origin, so that 0 is the only point in that neighborhood. Okay. So, that proves our proposition. So, it took quite a while, but this is an important proposition. As a corollary, we get the following: if K is a number field of degree n, then OK is a free Z module of rank n. Right. So, that is an important corollary we get. This is property 3 of the definition of lattice, and so we get this from 1 and 2. Okay. Now, we have a lattice. So, our standard notion of lattice is is Zn contained in Rn or Z squared contained in R squared, Z2 contained in R2, right. But there can be different forms of lattices. So, you can have a hexagonal lattice in R2, you can have a lattice that looks like a parallelogram, and it could be long in one direction and short in another, etc. So, we want to understand how R lattice OK sits inside Q to the n, but this is not a well defined question, because when we identify K with Q to the n, we had to fix a basis of K, and once we make a choice we have to say how our answer depends on this choice. Okay. So, can we give a statement which is independent of choice, and we can, as long as we are willing to go away from Q to the n. So, we have to go to real numbers or complex numbers. So, we are going to do the following. Okay. So, yeah. So, let sigma 1 up to sigma n be all the embeddings of K in C, right. K has degree n over Q. So, there will be exactly n embeddings. Out of this there are some real embeddings. Okay. So, we have already seen this when we did we already saw this particular statement when we defined norms, but now we see that let sigma 1 up to sigma r 1 be all the embeddings of K in C such that sigma 1 of K and so on up to sigma r 1 of K, they are all contained in R. Okay. So, out of these embeddings there will be some embeddings whose image will be contained in R and some embeddings whose image will not be contained in R. Okay. And if sigma I of K is not contained in R, then sigma I appears in a sigma I composed with complex conjugation gives a different embedding of R, sorry, not of R, of K in C. Okay. This means that sigma R 1 plus 1 and so on up to sigma n, they appear in pairs. Okay. So, I will denote n minus R 1 to be 2 times R 2. Okay. And what are the pairs? I will arrange them as follows: sigma R 1 plus 1 and so on up to sigma R 1 plus R 2, and then the complex conjugation of this. So, sigma R 1 plus 1 bar, which is sigma R 1 plus R 2 plus 1 and so on up to sigma R 1 plus sigma R 1 plus R 2 bar, which is sigma R 1 plus 2 times R 2, which is sigma n, right. So, sigma I bar is sigma I composed with complex conjugation. Okay. So, the non-real embeddings of K into C, they appear in pairs. Okay. So, we say that sigma 1 up to sigma R 1 are real embeddings of K, and then sigma R 1 plus 1, sigma R 1 plus R 2 plus 1 as a pair, etc. up to sigma R 1 plus R 2, sigma R 1 plus R 2 times R 2, these are complex embeddings. Okay. So, complex embeddings there are 2 times R2, but we somehow identify the pair sigma and its complex conjugation. So, you consider the map sigma from k to c to the n, and what is this map? It takes any alpha to sigma 1 alpha, sigma 2 alpha and so on up to sigma n alpha, right. So, this is a natural map that we can consider from k to c to the n. There is no choice of basis involved, the only choice involved here is how you order the embeddings. Okay. So, we call this map sigma for now. Okay. And we want to understand the image of k and the image of OK under this map. Okay. All right. So, what I am going to do next is I am going to name this map, image of this map. So, let V be sigma of k tensored with R. So, this tensor product is over Q. Okay. So, you see sigma of k is contained in C to the n, but I take its tensor product with R. So, that is my V. Okay. Now, I want to find out what this V looks like first. So, here is a small lemma that tells me what the V looks like. So, this is sigma of k is a vector space over Q, because k is a vector space over Q, right. And when I tensor it with R, you get a vector space over R, and I want to find, first of all I want to know what its dimension is. Okay. So, V is a vector space over R of dimension n. Remember, n is degree of k over Q. Okay. I have been using the same notation n throughout, and its degree of k over Q. All right. So, how do we prove this? Well, what we know is that for 1 less than or equal to I less than or equal to R1, sigma I of k is contained in R, right. That is what we, that is how we defined sigma 1 up to sigma R1, right. These are the R1 real embeddings, and then for I between R1 plus 1 and R1 plus R2, sigma I of k times sigma I bar of k, this thing is contained in R2, right, because they are both determined. So, this should be a comma, I mean depends on your notation, but I want to write it as a comma since I am writing it as a tuple, right. So, whatever this number is, this is its conjugate, right. And so, so it is contained in R2, which means now you just count how many there are, right. So, there is 1 for each real embedding, 2 for this pair of complex embeddings, and so dimension of V is less than or equal to R1 plus 2 R2, which is equal to n, right. That is how R1 and R2 have been constructed. All right. So, this is inequality in one side. I want to also show that dimension of V is greater than or equal to n. Okay. So, how do I do that? So, I have sigma from k to c to the n, right. This is an injective map. So, if I restrict this to OK, this is a map again into c to the n, and this is injective. So, sigma restricted to OK is injective, right. And you take it as an exercise, an easy exercise, that sigma of OK is discrete in C to the n. This is just like what we did before about at the beginning of today's lecture. Okay. And we know that sigma of OK, it also spans V. Okay. And because sigma of OK is discrete in C to the n, this is discrete in V. Okay. Therefore, sigma of OK is a lattice in V. And what is the rank of this lattice? Rank of sigma OK is same as rank of OK, which is equal to n, right. And so, if sigma of OK is a lattice in V, we get that dimension of V is equal to n, right. Okay. So, here I need not have proved that OK of sigma, I mean this step is kind of redundant. So, let me put this in a bracket and write it as greater than or equal to V, because and we already proved that it is less than or equal to n. So, dimension of V over R is equal to n. Okay. So, that proves our lemma. Now, what does that tell me? It tells me that V is isomorphic to R to the n. Okay. I am not going to choose this isomorphism, I just want to notice that there is an isomorphism like this. And now, we are in a position to ask this question, because now we have not made any choices except the ordering of the embeddings. So, so question, what is the shape of sigma OK, which is isomorphic to OK in V. Okay. So, in particular you can ask whether it is sort of very thinly spread out or thinly spread out in one direction. One of the ways to capture this shape, but not of course not tell everything about the shape, is to find its volume. Okay. So, the co-volume of this lattice, which means what is volume of R to the n modulo this OK. So, now I will stop writing sigma and just write this. Okay. So, this is a well defined question. Of course, it does not tell you the exact shape of the lattice, but it goes some way towards telling you what it sits like. For exact shape, we will have to find integral basis of OK, and that will be done subsequently in the course, but for now we want to understand this. And for this, one approach one could take is to look at measures on R to the n, a natural measure on R to the n, and then ask this question about volume. So, the reason I put volume in inverted commas is to have a good notion of volume, you need measure on R to the n, and so I should tell you what a good measure on this R to the n is for this question to make sense, but we are not going to do that. I am just going to give you a definition which is volume when you put an appropriate measure, but we are not going to do that measure theoretically. So, what I am going to do is you define M as follows. So, this thing is sigma I of alpha j. So, here 1 is less than or equal to I and j less than or equal to n. So, we know what sigma i's are, these are embeddings of k into C, and what is alpha 1? So, alpha 1 up to alpha n is a z basis of OK. So, again it looks like I am fixing a basis, but the eventual thing will be independent more or less up to a sign of this basis. So, I take this matrix M and I define discriminant. So, this is a very important invariant that you should know, discriminant of K to be it is usually denoted as dk. So, this is determinant of m whole square. Okay. Another way of writing this is its determinant of m transpose times m. Okay. This is also often called absolute discriminant. Okay. So, this is also called absolute discriminant, because it is over q, right, and later on we will also define relative discriminants, which will be for other extensions, okay, discrimin and a and t. Okay. All right. So, before I stop, let me give you an exercise for today. It is to prove that dk is equal to determinant trace from k to q of alpha I alpha j. So, the notation is as above, and this straight away tells you that determinant is actually discriminant is actually an integer. Okay. So, hence dk is an integer. All right. So, what we did today is we finished the proof of the fact that OK is discrete in q to the n. Then we want to ask how this discrete lattice sits inside q to the n, but we saw that this is not a well defined question, because we had to fix a basis to get this lattice inside q to the n. So, we wanted an independent basis independent definition of what a lattice of a lattice in either q to the n or r to the n, and we saw that this can be done in r to the n. Okay. And then it makes sense to ask these questions about how OK sits inside this r to the n, or what is the co-volume of OK in r to the n, and to that end we defined this discriminant. So, in the next class we will study properties of this discriminant.